Hello and welcome. My name is Bob Falconer. I'm a chartered civil engineer with over 40 years experience in inspecting, observing, researching, testing, assessing, repairing and strengthening masonry bridges, and in lecturing at the University of Greenwich about the history, theory and performance of these bridges at undergraduate and master's degree level, and on CPD courses to practicing engineers. Because every bridge we've looked at has been different, it's been a source of endless fascination. I'm not arrogant enough to call myself an expert, but I've picked up a few things along the way. In this, the first of a series of presentations, I'm going to talk about the masonry arch repair and strengthening system. We call it the MARS system. The presentations are essentially a PowerPoint lecture I gave to the Institution of Structural Engineers on the 25th of April 2022. I am a director of Goldhawk Bridge Restoration Limited, the company that installs the system, though I will be giving a personal perspective rather than a company one. One of the reasons for these presentations is that we're aware of a number of false statements that are circulating about the system, some of which came out in the lead up to my talk, and I hope to dispel these myths. A leading figure in the bridge world has stated that the system is a beautifully simple and elegant solution, and he wished he had thought of it. In this presentation, we'll look at how all the components of the system work together, and then we'll look at the cost and environmental advantages. The next presentation in the series will illustrate the application of the system using case studies. It's much longer than this one, so I've split it into parts 2A and 2B. The final presentation will cover the theory, testing and validation of the system. Though I may do further presentations on parapet strengthening using the MARS system, the history of masonry bridge development, giving rules of thumb that were used, etc. And I may even do one on the pros and cons of alternative strengthening systems. Probably more the cons. The MARS system is essentially a grid of stainless steel reinforcing bars that are inserted into the underside of a masonry arch in order to bridge cracks and, if necessary, strengthen it. I should say here and now that I'm very much against putting unprotected reinforcing steel in masonry bridges to locally repair cracks. If cracks are stitched without addressing the cause, then they will, in time, just simply move to an adjacent location. The stainless steel that we insert spans the whole of the bridge transversely and circumferentially. That's transversely and circumferentially in a grid pattern so that there's no place for the cracks to move to. It also uses small diameter reinforcing bars so there's minimal effect on stiffness, both locally and generally. Also, our bars are completely encapsulated in adhesive grout in slots to protect the stainless steel from the salt water that percolates through masonry road bridges. Our adhesive grout is called MARFLEX, and it was developed specifically for our purpose by Newfins of Tyne and Wear. It's essentially the same material as has been used for many years for expansion joints in road bridges. It's therefore impervious to road salt and moisture. It's thixotropic so it doesn't fall out of the slot when pumped in, and it has to be the stickiest stuff ever invented. It sticks to absolutely everything. Spectacles, PPE, etc. etc. The staining is impossible to remove. It sticks better in the damp than in the dry, so it's ideal for the conditions we face. In the very unlikely event that repairs need to be carried out, then the MARFLEX can easily be cut out and repairs can be effected. At our proving test for the system at the Transport Research Laboratory, at failure, there was no loss of bond between the MARFLEX and the steel, and between the MARFLEX and the brickwork. It was the surrounding brickwork that failed in shear. In our grid, the circumferential bars strengthen the bottom ring of brickwork. That's these bars here, circumferential bars. We've got two in this case. That's them, and then this is the transverse bar there. and there. Circumferential bars concentrate the thrust in the barrel into the bottom ring. If we left it at that, this could actually weaken the barrel. In fact, I've actually demonstrated this in tests at the university. This is why we insert radial pins into the barrel at regular intervals. These are the radial pins, there and there. These prevent differential movement between the rings and allow the barrel to work as one unit. Our software calculates the shear between the rings and allows us to insert an appropriate number of pins. As the pins also help with the positioning of the bars, we invariably insert more pins than are necessary to resist the shear between the rings. As we're not faced with the problem of carbonation in masonry, and as our stainless steel is fully encapsulated, the cover to the steel is not that critical. The moisture comes from the fill side in any case. Also, the underside of bridges is generally more sheltered and not so much subject to freeze-thaw. We did install the system into a road over rail bridge about 20 years ago. The bridge had been pointed with cement mortar. There's nothing we could do about that. We were asked to look at it again recently, and the brick in the more exposed areas had suffered from serious spalling due to the moisture being forced through the bricks and freezing. The MARFLEX system, however, was still working perfectly. The installation allows for a 2 mm gap at the edge of the slot so that we can point with epoxy mortar combined with brick or stone dust to effectively hide the slots. That's this part here. However, as we can colour the MARFLEX to accurately mirror the colour of the brickwork, most clients tend not to opt for the extra expense of this option. An aspect of masonry road bridges that doesn't appear to be much appreciated is that they act as large pressure relief valves, relieving the water pressure in the fill. As an illustration of this, we can take a concrete portal bridge over the Leeds and Liverpool Canal in Skipton in North Yorkshire that I had the pleasure of inspecting. This was many years ago, and we did our work from the roof of the narrowboat you can see in the foreground. The bridge had drainage holes in the spanning slab along here, over the canal, and it had been sprayed with a concrete spray, and these drainage holes were blocked up. Traffic over the bridge pumps the surface water into the fill, with the asphalt surfacing acting as bellows. As a result, high pressures can occur within the confines of the bridge. In this case, the pressure of water in the drainage holes had blown the sprayed concrete layer off in large sheets, as can be seen. One could have caused serious injury to anyone who happened to be passing under at the time. This is the sheet that was blown off. It's actually quite a small one, and I think that's the drainage hole. The other holes are from us trying to take chloride samples, but having difficulty finding a clean hole because of the congestion of reinforcement. We've also cored into a concrete abutment and encountered water coming out with the pressure of a fireman's hose. Drainage systems do invariably clog up. Masonry bridges don't have this problem as they allow pressure dissipation. This is why strengthening techniques such as gluing glass fibre sheets to the underside of a masonry bridge are a bit of a nonsense. They would create a build-up of pressure behind them, which would mean that the sheets would be forced off after a few years, so they can only be treated as a short-term solution. These sheets might work well in a laboratory with no water pressure and fresh mortar, but in practice they're not such a good idea. The MARFLEX system allows masonry barrels to continue to breathe. It would be okay if the barrel had waterproofing over the extrados. However, we've installed the MARFLEX system in, I estimate, over 300 barrels, and we haven't found any evidence of waterproofing in any of the cores that we've taken. Waterproofing by grouting the fill over the barrel also wouldn't be effective, as you can never guarantee full coverage with grouting. It's also one of the reasons why barrels shouldn't be grouted with waterproof grout. You don't get this pumping action so much in railway bridges, as there isn't an impervious surfacing to act as bellows. It's thus important that the surfacing on road bridges is well maintained, so that the salty water doesn't get in there in the first place. It's also why loss of pointing in a masonry bridge is common, though in theory the percolating water isn't under pressure. This drawing is a typical example of the layout of the system. It's actually a bridge in Oxfordshire built around the 1800s. In this example, the thickness of the barrel is not the same as that shown at elevation on any of the spans. In fact, the south span, the thickness is actually a half the thickness that's shown at elevation. So that's the thickness at elevation. This is the thickness of the span, 150 millimeters. The moral here is never to take the thickness at elevation as the actual thickness of the barrel. This is a stone bridge, though I have to say that brick bridges are a bit more consistent. Stone bridges do behave very differently to brick bridges, but again, this isn't really recognised by the codes. You'll see that the MARFLEX system from here extends from the parapet spandrel wall to the parapet spandrel wall at that side, because lateral pressure from the loading and from the fill tends to push the spandrel parapet wall away from the barrel, and we try to correct this by tying the walls together with our transverse bars. We also introduce bars at 45 degrees, as you can see here, to try to counter rotation. Spandrel parapet walls each provide a stiff vertical plane, there and there, stiff vertical plane. The barrel inside the plane acts as a jelly mold under traffic loading. These two are incompatible with each other, and in well over 90% of the bridges we look at, there's a crack that runs around the barrel inside the plane of the spandrel parapet walls. This incompatibility is why it's unsafe to treat a masonry bridge as a 3D structure. The MARFLEX system bridges this crack to hold the bridge together, but there is flexibility in the MARFLEX which prevents fatigue in the reinforcement from the minute relative movement across the crack. The amount of reinforcement is designed such that the bridge can just take the design load for each span. In this case, for the middle span, it's two 6mm stainless steel ribbed reinforcing bars at 340mm centres, and then we've got different arrangements for the other spans. When installing the system, we always assess the capacity of the bridge for the situation where the slots have been cut but the system is not yet effective. We term this the temporary condition. The important slots here are the transverse slots, because they could coincide with the critical location for the particular loading we're looking at. The transverse slots are 12mm wide and typically a maximum of 26mm deep. This is equivalent to up to a 26mm loss of mortar in the barrel. It's very rare for this to reduce the rating of the bridge. In the event that it does so, then we'd normally install a width restriction on the bridge to prevent large vehicles from using it while we were working. The MARFLEX only takes a few hours to cure to the strength that we require. If a weight restriction has been necessary, it is retained with the bridge acting as per the temporary condition until the cure has taken place. We usually retain a weight restriction for at least 24 hours to be safe. To illustrate the environmental factors as well as costs, I think it might be a good idea to look at the controversy over the infilling of Great Musgrave Bridge in Cumbria. The infill comprises mainly aggregate which has been described as recycled. This is better than quarried aggregate, but still requires huge amounts of energy. Then there's the transport. Not only does this require huge amounts of fuel, the effect on those affected by large lorries thundering past their doors, emitting noxious gases and particulates, is not very neighbourly. The site itself requires large plant with corresponding emissions to move aggregate into place, and then there's the use of concrete, which is not exactly environmentally friendly. This contract reportedly used over 1,500 tonnes of aggregate and over 100 tonnes of concrete. They appear to put pipes, I think that's one there, under the infill as animal runs. These pipes will inevitably get blocked, forcing the fauna over the road above. The website Habitat Matters should be an essential resource for all civil engineers, as we have a huge effect on the environment with the work we do. And rather than mechanically filling in an environmental impact form for a project, we need to have a serious understanding of this impact. The MARFLEX system, on the other hand, obtains its materials from North Wales and north of England, and our headquarters is in Slough in Berkshire. So we help employment in these areas and minimise transport, as everything comes from the UK. We only use small hand tools, which are hired from the area in which we're working, and scaffolding platforms that are also hired from the area in which we're working. Thus we enhance local employment and only need small vans for transport. And as our operations only work from under a bridge, we rarely require road closures, and the considerable environmental impact of traffic detours is avoided. The MARFLEX system also avoids costly diversions and/or temporary support of services that run over the bridge. If these services include fibre optics, then these costs can easily run into hundreds of thousands of pounds. This is an example of the finished MARFLEX system. I'm sure you'll agree that it not only looks good, but it also gives the public assurance that the bridge has been strengthened and is safe to use. The beauty of the MARFLEX system is that it uses all of the inherent strength of the arch barrel and only adds sufficient reinforcement to bring it up to the required capacity. Thus, no part of the structure is rendered redundant, and only minimum quantities of materials are required. The cost and energy saving advantages of this are enormous. The finished infill project is turfed over and hides the fact that it's an extremely environmentally unfriendly exercise. It also shows disrespect to the work of those who designed and built the bridge. There will always be a void under the bridge as the imported fill settles. We will see later how neglected bridges crumble and die, and when this bridge collapses into the void, we just hope that no one is driving over at the time. The cost of infilling was reported at £123.6 thousand. I don't know if this included site setup and design fees. We were asked a quote as an alternative to bridge infilling, and the cost of the MARFLEX system came to under £50,000. We also included for pressure pointing the masonry, as a great deal of mortar was reported as missing. We will come to this later, as the pressure pointing probably needn't have been included. Our total came to just over £86,000, which is much less than the infilling. It would have been just over 80,000 if we didn't include for the pressure pointing. So that's even less than the cost of infilling and less than the cost of removal of the infilling, which has been quoted, 90,000 has been quoted as a figure to do this. The MARFLEX system in itself doesn't require maintenance, and so the bridge would only require the normal inspection routine for the rest of its life. It should be noted that Bill Harvey was commissioned to assess this bridge, and he concluded that it was actually okay. We came to a slightly different conclusion in that we found that it needed minimal strengthening to enable it to carry the required loading for public roads, plus SV80 loading. Our assessment assumed the mortar loss that had been reported. Bill Harvey had access to more accurate information, and he noted that the mortar loss was not as bad as had been reported. National Highways estimate that the total cost of removal, repair and strengthening would come to an eye-watering £316,000 to £431,000. This is in comparison to our elegant and simpler solution, which maintains the character and aesthetics of the bridge for generations to come. Thank you for watching. I hope I've given you a good insight into how the MARF system works. The next presentation in the series will look at applications of the MARF system to illustrate what we've been talking about. It's much longer than this one, so I've split it into parts 2A and 2B. We'll then look at the theory of how the MARF system actually works and the testing and validation work that has been carried out.